So I'm very excited to introduce two representatives of one of my favorite and most used online or e-commerce searches, at least, which I'm using for, I think, 25 years now. And yeah, welcome Arnab Dutta and Gleb Polushin. They talk about using AI models to improve user experience at eBay search. Thank you.
Thank you, Matthias, and hello and welcome everybody. So today, me and Gleb, we're gonna walk you through a little bit of what we are doing at eBay Search. We would like to start off top-down approach. So we would like to say like what all AI applications we do have at Search, and then dig a little bit deeper into like one particular aspect and what has been done so far. And so with that, I would like to give you a brief overview what's coming up. So basically, in general, like how we are handling AI in what verticals, what are the products we are trying to use, and take a bird's eye view of search as such. We cannot get into so much of details here. Then we look into like one particular module and a little bit more deeper, and maybe some of you are working already on these aspects. Maybe this may help. So we are here to share our experience there and hope that helps. So we have a very dedicated customer already. Thank you, Matthias. Wish you could tell that again on camera. Maybe my PMs would be very happy. But in general, like so eBay is like really one of the oldest e-commerce platform, and we do have 1.8 billion live listings. So live in the sense that they are right now there, because people like they have auction items, everything, and they do decay over time and so on. So like almost over some 133 million active buyers all over the world. And on mobile itself, we have like almost $11.6 billion like of a volume in terms of business. Now, talking of AI at different steps. So basically, all these verticals you see here, like you consider even thinking of buying something at eBay, you start browsing. It's like a journey for the user. And we try to incorporate our AI modules at these different stages, starting with search. So it has been done in the bold box here. So I would like to dig here a little bit details. So a lot of things happen in the search. So basically starting with how you're reformulating your queries, query understanding, some of you mentioned already, I think Andreas in your beginning slide, then spelling correction, like segmentation, how you can do smart category detection. iPhone 12 is cell phone category, iPhone 12, Gorilla Glass is accessories categories. How do you come up with these kind of things? Image search, you take a photo of this cup or this HD camera, and it will just give you like what are the relevant results. Of course, it doesn't end there. You go ahead, do a shopping, and you complete the transaction. So at every step, you have like even like for shipping, you have estimated delivery time and so on. So now search science at eBay. So essentially, it's like searching a needle in the haystack, right? So it is indeed that difficult because you cannot really have that exact relevant item. You may have the relevant item missed sometimes. Sometimes it may happen that the items which are popped up are not so relevant for the users. It's always like a double-sided sword for you. Why, or let's say, what I'm trying to dig here now is like search in eBay is quite important because it really drives a lot of business. It's like we're talking of some few million dollars of US money. And almost we have a lot of searches per day, like almost 400 million searches, and it's a huge amount. And we do have to verify like always almost 100% uptime. And this is one of the really largest scale ML application we have in the industry. Now let's take a very broad overview of like how search and how the components are working and why we are trying to focus in one particular aspect. You start off with a very simple search item, Bosch drill, and you are quite happy to see some items popped up. You have some aspects like attributes of the items you can filter on. You can see like what are the most probable category this item or the query should belong to because you're looking into cordless drills. But behind the scenes, like there are two major backbones, basically the backend and the search science. So they're involved in the recall and the relevance part. Recall is like what are the items should I get given the query, and relevance or the ranking team is responsible for like how can I optimally rank those, because in this ranking part we are not fiddling around with the inventory anymore. We are having a set of items and we are just ordering or just customizing the ranking. So like ML are at play there. And the second, like the backbone of everything is basically our indices, right? Like we have inverted indices, probably a lot of you heard of it. So you say like, okay, iPhone version document 23, 99, 223, and so on. You have like a huge indices like that. And there are some services on top of it, which says like, okay, how do you fetch those indices efficiently in like under milliseconds? Now, To do that, you see like one thing I'd like to draw attention. This is the entry point to the system. You search something and you fetch some results. Now what happens if something goes wrong here? So there comes the spell correction model. And this is kind of quite user facing, quite at the forefronts of our users. Like anything, people are in a rush, people type on while moving on the street or something, there could be a mistyping. You see here, I don't know how many of you noticed, like there is a misspelling under bridge. So this is like the subtlety of the things, right? So here, this kind of things might happen. For example, like if you run very fast, like look through, okay, it's iPhone. Okay, no, there is no H. And you see there are no results for iPhone, right? So this is horrible experience. Like, okay, how bad it is, like, okay, I'm pretty sure like it's an iPhone and why couldn't you return me some results? So now that's why spelling correction in general is quite important for eBay as such, because this is bringing, like we do have a lot of spelling corrections, roughly around 10% from our search logs. And this directly impacts our null and low results. So like if we could fix this subtle element, like this spelling mistakes and stuff. So null and low queries are basically the search results where you have really 0 results, or at least below some certain threshold, right? This also, like instead of iPhone, if you like look for the real iPhone, you would see more relevant results. You're exposing your inventory rightfully to your customers, so which is really intended. And of course, people are always using a lot of other platforms, and it's expected that search should be smart enough to deal with such subtle mistakes. Like it's not the problem that oh, it's not my not my problem, so like somebody else should fix this. No, like you type something horrible in Google, it rectifies it in a very smart way. So that's the expectation people come to at eBay. So now in general, like I'd like to like broadly classify our approaches. So like one on the left-hand side is a bit of a dictionary-based approach. So this is, we know some usual mistakes which might happen, and we try to rectify that based on like a static dictionary. Good, works well, no latencies almost. But the problem is, what about new items? Like how generative are you? Not at all, right? On the right-hand side is basically an ML-driven model which tries to improvise on the fly. So you have a misspelling and you try to see like, okay, this, given the context, given the preceding and the succeeding letters I have, I know how to formulate this in a better way. So now this already puts it in a timeline frame, because this is not a new work we are trying to do, or we are not trying to solve a new problem, but it has been. So that's what I'm trying to stress here. Like it's an age-old problem. It's quite critical for like a search engine, because that's where your business lies. You have a misspelling, people will just say, I'll go and buy to your competitor, right? So that's not intended. You would like to hold on to your customers. So in the beginning, like around 2014, we had like noisy channel models. Basically, you're predicting A followed by E followed by G, what's the probability and stuff like that. Second, we started looking into deep learning models in early 2021. Then we made some improvements in late 2022. And now what's next? So what could we do more? Like we already have a deep learning model. So there could be like, we can start looking more multilingual aspects, like we can try to fix all different foreign languages, not just English, or it could be like even advanced model paradigms. Like what could it be? So now I'll just take a small detour and just give you the audience like a very brief like a overview. I think most of you know this. So there are like two general models of this approach. So general approaches to this modeling, sorry. So like one on the left is sequence to level. So basically you have a sequence of input and you'd like to predict a label for it, like A or B or C, or whatever it is. So that's why the name comes sequence to labels. And sequence to sequence is more like you have a set of sequence, and it could be like a text, could be audio, could be some stream, and you output another sequence, right? So that's why the name comes sequence to sequence. So sequence to model, like this is a very high level. So basically on the bottom is like a Windows 11, which is totally misspelled. And what it tries to do is like you have some BART-like encoder models, and you say like, okay, I would like to drop this, delete. So basically these are the labels getting to predict. So this is like the labeling operation. So it's like a classification problem, right? So yeah, and this is what we have for the moment. There is a paper here. This is done by one of our colleagues, Mengi, and you can go ahead and read about it. So basically, essentially, the idea is the same. So like we have casual dress with a misspelling here, and the model predicts like, okay, keep this character, replace this with A, add some space, and so on. The general idea being it's like sequence to a label. Now, what could be different? Like sequence to sequence, the same thing. Now what we have like is a transformer model. Like you have encoder and a decoder. So basically it encodes your state here, and you just try to fit that encoder state. So basically this is a bit old school in that sense. Like, yeah, most of you probably know this. and you have your predicted or the sequence, which is the target output. Basically, the target sequence is spit out. Now you understand that. So now basically, like, we looked into a different paradigm. It's basically the fine tuning. So, and since there was a lot of buzz around language models and large language models, so we also started looking into that area, like how efficient it is. So like just a primer on this, the pre-training is essentially okay. So pre-training is essentially like you have a large set of documents and you try to train it with your resources. This might not be an optimal solution for your scenario. It requires hardware, it requires a lot of GPU power and a lot of manpower as well. And on the other side, you take those kind of models and you try to fine tune it. Fine tuning is like basically you take a recipe for making pasta, and then for your use case, you try to do some fiddling around, try to change some spices and do something around it. So you just take the mother recipe and try to tweak it in your favor. So that's the beauty of it. And what is important here is like it just requires small corpus of data with some few sample seeds. It's quite easy to like manipulate this mother model for your purposes. So basically you can have a task X, you can just send some data and you can just fine tune for your purpose, or you can have a task Y and you can do the same. So with that, I'll hand over to Gleb, who will follow up the next slides.
Yeah, hi. Thank you. Let me continue. So when we were thinking what to do next, like remember on the one of the first slide with the timeline, what to do next, we decided to consider a change of the architecture to sequence model, because now we have sequence to label. And also we decided we wanted to take advantage of using pre-trained models. And in order to evaluate all the approaches, we considered them in terms of important characteristics for us. Like, for example, sequence to label model have this huge overhead for customization because we need to construct this label space with all this insert and replace operations. Also, we thought that we could benefit from these models having some external world knowledge, like brands and I don't know, celebrity names, because we see that a lot in search queries. Also, we talked, as far as we operate in different languages, it is important for us to make, it would be nice to have one multilingual model for all the languages, for all the sites. And as far as this model works in real time, the inference latency is also an important thing for us. And considering all of the above, despite the bad inference latency speed, we decided to go further with the fine-tuning of pre-trained sequence-to-sequence models. So what model we took? There are plenty of different sequence-to-sequence pre-trained transformers. We decided to take T5 and BART. You probably heard about them. T5 is an encoder-decoder model which was trained on different NLP tasks, supervised and unsupervised, like text classification, summarization, and so on. And BART is another similar architecture encoder-decoder model, which was trained primarily on denoising the input sequence. So we took models of different sizes, also took multilingual versions of them, MT5 and MBART, and continued to experiment with them. So what about the data collection? The main source of our data, I hope you can see it. On the left side is a natural data, the cases where users corrected queries by themselves. In order to collect such cases, we took like all sequences of a query from one user, collect all the pairs, and then filter them with different heuristics like an edit distance in order to get really corrections, not just different queries. There should be improvement for a second query. It should be like improvement in recall, in some click important metrics, and so on. And that's how we obtain these pairs of misspelled query and corrected query. Also, in order to enrich the data set, we calculated these error probabilities from the natural data and create synthetic mistakes for just usual queries. And of course, enriched with the correct queries in order to make model learn not to correct when we don't need it. And we had human labeled data set with these corrections for all the languages. Like, for example, this how data sample look. We have correct pairs, we have two types of mistakes, the natural one from the users and synthetically generated one. And so we took these models, we took this data, and we fine-tuned them on our data set. And here the results what we got on offline evaluations. On the left side, at the bottom, there is a baseline, our current sequence to label model. So all the sequence to sequence models are better in terms of the precision recall and all these quality metrics. Of course, they're slower, like bigger the model, the better the improvement. What we took from this table is that BART base is kind of a best trade-off for us in terms of the quality improvement and the inference latency. And we decided to experiment with it further. And on the right hand, we talked about this multilingual thing as far as we operate in different languages, and we decided to train multilingual model on the mix of 5 languages. And here the comparison, like it was one model trained on 5 languages. For each language, we had our production model, which was trained only for specific language. So we're like comparing one language versus 5 different languages, 5 different models. And we see that model could benefit also from this multilingual thing. I think one more reason also for that is that there are a lot of queries with brands with some entities which are the same across all languages. That was also another exploration for us. We didn't thought about it. Yeah, so basically, does it work? Yeah, here are some cherry-picked results with the corrections, with the examples. For example, in the first 2 cases, BART base recognized entities better. Like in the first query, it recognized Christian Dior. In the second, 7 dwarfs. We believe that probably because of the external knowledge. In the third row, like also BART base was better. So we think that because of the better context handling, because of sequence to label, just saw something about the clothes, jeans, and already say dress. And BART base is a little bit smarter in this case. And of course, there are cases when the both model are wrong, and when even our old current production model is correct. Yeah, but in general, BART base is better. So let's remind what we talked today about. We talked like in general, the overview of eBay search. We talked in details about how speller correction functionality works at eBay. And just another case, how we can use fine-tuning of language models for e-commerce. We're doing right now, we took this multilingual model, we took this BART base, we experimented with speeding up the inference because the model should work in real time with different techniques like the model pruning, distillation, and so on. Like we are on our way to deploy it and run an A/B test. And also in future, we would like to use LLMs, so like a large language model. Maybe a few years ago, T5 and BART base could be considered less large. Now it's definitely not the case. So yeah, we wanted to try it also. And we also wanted to mention our other colleagues who worked with us on this project and or worked before. Yeah, thank you. We would be happy to answer questions.
Thank you for your talk. You said that you have took half a year data, like log data, and a year data of queries to train your model. Was it really so necessary as every day you have like millions of points of data?
Just, I'm sorry, could you repeat?
So you said that to train your model,
Yeah.
you took data of half a year, yeah, 6 months of query refinement logs and 1 year of request queries, like giant amount of data.
Yeah.
Was it necessary? If you have like every day millions of points of data in this logs?
I don't know, it worked well, just for taking the long period, we get more queries like about different topics, remove this seasonality factor and so on.
Exactly. That's the point. Like you look so back, like look back so much that you kind of account for your seasonality trends. You don't suddenly see some biases, for example, Easter related queries, Christmas holiday queries. So you distribute it over some period of time. data is God. I mean, why not? I mean, the more you have is, it just makes your model less biased towards one particular trend or things like that.
Yeah, thank you guys. Awesome work here.
Yes.
I have one question. So if I understood it right, you get a sequence of characters and your model predicts a different sequence, potentially a different sequence out of it. Did you already consider to, let's say, have a shallow first retrieval and then only use the expensive BERT model just to re-rank these candidates and pick, let's say, the best one out of it?
We don't have the time. We have to return it back in milliseconds. We really don't, cannot afford to do like a two-step process. Like initial thought was like, okay, if it's so expensive, maybe we can have a candidate selection and they do something. But you type something, users are expecting it, because that's the proven trend or like the user behavior we have experienced. Like if anything slows down, like people are just gonna break it easily.
I challenge the fact that it is slow. Because for candidate retrieval, there are super fast algorithms out there without the heavy stuff. And then to bring the right one in top, the right spelling correction out of these candidates is way easier and less expensive than running the full sequence. Okay, but thank you.
Yeah.
Hi. Thank you for the great presentation. My question is actually handling the mistakes. So do you have a safeguard to make sure that you are not changing the corrected queries to something else?
Safeguard as such, in the sense that, yes, you're right, it can go wrong because it's a predictive model. And what we try to do is safeguard in the sense that we do not try to totally eradicate the user's initial input. Maybe some parts are wrong because this is just not like one module working alone in solitary, right? There are recovery strategies. There are like token droppings happening. There are like smart query rewrites happening. So we keep them as it is. So the idea is like this, or like the corrected one. So we try to augment the original behavior with the corrected one. So even if the corrected one is not optimal enough, right? So it is possible. You still see, the users would still see some relevant results coming up. Could be better, but still we don't like totally say like, hey, I don't understand, and this is totally relevant results for you. That's not gonna happen.
Yeah, like here you can see that we're searching both for the misspelled one and the corrected one.
Yeah, we did run some exhaustive A/B tests on top of this because our hope was just put this out in the wild, let this particular modeling work alone. Then we saw some matrices dip down, but okay, just to like totally go against the existing procedure is not so elegant. Maybe we just do like a union basically of these two variants. That worked.
Hi. So you mentioned somewhere a 10% number, that there are 10% misspelled queries. I was not sure if that's your upper bound or that's the number of queries you're correcting today.
Yes, that's basically our like correction side. Basically, like 10% in general we see from the search is like having spelling errors.
So is it basis your data that you have found that only 10% of your queries are misspelled, or do you think they're higher?
No, it's based on the data.
Okay, then coming to my question, how did you identify those 10% set of queries? How do you know out of these 100 queries, only these 10 are misspelled?
So we did run some like human judgment rounds, like we did run some samples, and then we had some dictionary based approach to say like, okay, is this a dictionary term or something like that, or I haven't seen this ever before. So there is a bit of lookup / human judgment happening there to come off. You cannot never come up with, like with 400 million searches, you can never come up with an accurate number. It's basically a guesstimate in that sense. Okay, on this sample, we see this kind of a behavior. So plus minus, I don't know, 0.5% is the error range. So yeah, it's basically to know like, okay, how wild it is. Is it like 0.001% or is it like 50% of them are having error? So just having a range, so that helps.
Okay.
Yeah.
Thank you for your talk. in an old good Elasticsearch way of doing the suggestions, with a couple of tricks, you can be sure that all the suggestions are actually generating some results if you search for them. But with the generative models, they can generate you a lot of different wonderful suggestions, but none of them will actually result. If you search for them, none of them will just yield any results. How are you dealing with this problem?
There are two parts to this answer. Like if you go like the classical LLM interpreting like prompt tuning way. So like there are smarter ways to tune your prompts, right? Where you say like I am explain the results and you tell me like, okay, these are the results. But using this approach, we do have a dedicated ranking team, and they would. So basically, our job is to fetch whatever is possible. We are the recall science team. So basically, here's the input. Here is a bunch of documents, and the ranking team takes a set of documents, runs some modeling on top of it, and they have extremely efficient like features. So, okay, this is bad, this is good, this is relevant, non-relevant. Okay, here is your final dish. So we are working in two phases. So for us, I mean, we are not so strict because our always goal is fetch from the inventory, expose everything you can, what matches. Yeah.
And also, of course, for the training data, we carefully filter the cases where the corrected query is worse in these terms.
So I was playing with eBay spelling correction and found some very bizarre results.
Sure.
So I tried headache pain with pain spelled P-A-N-E, like a pane of glass. And it came up with headache panel. Then I tried headache pain spelled correctly, and it corrected that to headache paint. Now, in fact, there are headache pain remedies. It did an or actually of headache pain and headache paint.
Yeah.
So I'm wondering, are you not doing word level semantic kinds of prediction?
The one you're seeing right now is still our old model, which has its.
I'm sorry, can't hear you.
The one you are using right now on production.
Yeah.
It's still the old model we have been comparing
okay.
against. So this is not the model live yet. So this
Got it. Okay.
Because you see in the last step, like we are still working on the inference part, and that's what Gleb mentioned.
Got it. Okay.
So yes, there could be inconsistencies, and really, this is not a nice behavior. Clearly, I can see that. But yes, I mean, this character level model is not really looking into like extremely long context back, because that's kind of the limitation of this LSTM based.
Right, but if it's doing it at the character level, then it's going to have trouble with long tail words. Like, so my classic example, which Google does a very good job on, is iron ore spelled like the rowing oar, and rowing oar spelled like iron ore.
Yeah.
And it corrects them, which I find very impressive.
Yeah.
Because they're both correctly spelled words.
You raise a good point, because like this is also like there are two kinds of spelling errors. Like one is like spelling errors, as you say, like you misspell chair totally, and you could be like t-shirt where you spell T-E-A. It's not a wrong spelling, but it's just like wrongly placed. Like that's not the t-shirt you're looking for. So that's kind of quite tricky, and this model would not be able to. Might be, we haven't tested it out. I'll be honest, we haven't tested it out loud there. Like, we haven't seen like how good it is to like handle position words properly. So if you see these examples, I really like this one. For example, 32 Abercrombie dressed, this like dress doesn't fit in there. It's basically a distress, like the torn ones, like yeah, so this is the power we are trying to leverage out of BART kind of model. So I hope you will be a happy customer soon. Yeah.
Iron ore, actually.
Yes. Yeah. Yeah.
Yes, one more.
Okay, so thanks for presentation. It was quite nice, I think. So I have a question about the training data itself. As far as I remember, it was consisting of two parts, right? One from the denoising part. And
I'm sorry, can you be?
Yeah.
So the training data consists of two parts, right? The first one was from the denoised, and the other one was from the actual like tracking data. So what was the proportion of that? Do you remember, like of the denoised data? And also for constructing the denoised data, which like did you use the tab queries or like the catalog data? Which kind of data did you use to do that?
Yeah, so the proportion of like synthetic generated errors was about, if I remember correctly, 20%. Proportion of correct queries, which model should not correct, was also about like 20 or 30%. And it was a mix of the most popular queries, just to be sure that we don't mess them up. And we call them torso queries, like the average queries. Yeah. Does it answer your question?
So the other question is like during these synthetic processing, did you eliminate also the misspelled queries? So the ones that you're also generating with the training data can also contain incorrect ones, right? So you might be denoising the incorrect query to another incorrect query. So did you do anything for that?
Or you
Usually,
mean like this examples, like where it's wrong in the first place, but you still generate like a wrong.
Yeah.
no, we should not, because for the synthetic generation, here we took only like so we call good queries, which produce high recall, which should be without any mistakes. Yeah, so we only change them.
Okay, with no further questions, thank you, Arnab. Thank you, Gleb, for the insights.
Thank you.